All right, welcome stats students to class prepared for Friday. What is that, April 10? So we're moving right along in chapter 13. I left my book at home. I think it's section 8. What I know for sure is that the title of the section is Goodness of Fit. So whichever section in chapter 8 is Goodness of Fit, that's where we're looking today. So we want to test the hypothesis here that a particular population has a certain form. And there are several ways we can specify that. We'll look at some examples. We could be interested in like the nature of the population. Is it normal? Is it exponential? Is it Poisson? Whatever. So the nature. And then once we are curious about a nature, then we need to figure out what the parameter values are. So we can make it sort of a vague hypothesis that it's exponential, period. Or we could be specific. We could say it's exponential with lambda, the parameter, equals 5 or something like that. The test will get run the same way, basically. It doesn't matter how much we specify as far as the mechanics of how we're going to run the test. The difference is in the degrees of freedom. As we will discover, we're going to use a chi-squared test here, just like we've been doing this is the third or fourth section where we've used the chi-squared random variable. And at the end of the last video, the video for Monday, there was not one for Wednesday, I gave a brief discussion of degrees of freedom. And the difference between those hypotheses that I stated earlier, with or without the parameter specified, the difference in how we run the test is going to be the degrees of freedom. Remember, we said every time we estimate a parameter with an estimator, the degrees of freedom goes down. And so that's where the difference will be. And so with that said, let's take a look. We're going to use Fi and Ei as before. That is, Fi is a frequency from our sample as we're just counting how many values have a certain property. And we come up with a number, F sub I. And then we're interested in Ei. If the null hypothesis is true, how many variables, how many sample values with that characteristic corresponding to the subscript I should we expect? Okay, and then as justified earlier, we can take those values, the observed value, the frequency, and the expected value, and turn them into a chi-squared, the details we've supplied in the past. We'll do it exactly the same way. We'll just subtract the values, square them, and divide by Ei, the formula we derived earlier. If the null hypothesis is true, Fi should be close to Ei, and so we expect a small contribution from that value of I. If it's not true, then some of them we would expect to be badly missed. That is, the expected number would be nowhere near the frequency. And so we get a big contribution from that value of I to X. Altogether, we add them all up, and then we compare it to chi-squared nu. And notice I've left nu sort of vague there. That's because it depends on if we use no estimates whatsoever, then nu would be n, the sample size. And then it'll come down for every parameter that we estimate. So here's how we're going to do this test. In general, number one, we're going to split the range of values. If we run the process as if the null hypothesis is true. So if the null hypothesis is true, then we know there are a range of values that we would expect to get from our random sample. And there's no hard and fast right and wrong way to do it, but we'll have a good idea. We'll talk about some examples. We're going to split that range into k segments. I think I would pretty much always use equal segments, but it doesn't really matter. You don't have to. I guess if I weren't going to use equal, I'd like to have a good idea why. Number two, we're going to compute theta I, the probability of a sample value being in a segment. And again, if null hypothesis is true, we know what the density is, or the PDF, and so we can calculate that value If no parameter is specified whatsoever, then we can't actually calculate theta I. What we would do is, and again, I'll show you some examples. We would replace the parameter with an estimate of it, our best estimator for it from our random sample, and then we would calculate theta as I, assuming that's the value of the parameter. Okay, number 3, from our sample of size n, we just count how many values land in each of our k segments. That gives us F1 through Fk, and then we calculate the expected value, which is the probability of landing in a segment times the sample size, n theta I. And then we compute x, that is, we just sum those up, x being defined right over there. We sum up all of those differences squared divided by EI. And then, we're ready to run the test. We compare it to chi-squared alpha for a traditional test with the appropriate degrees of freedom. Or we compute the p-value of the test. That's probably what I'll do. All right, let's do an example. I'll pause you while I set it up. All right, I have an example for us to work through. I'll set it up on the board here, and then we move to Excel, actually a Google Doc, which maybe I did it as a Google Doc. I can share it with you in case you want to. I don't know, maybe it's, no, anyway, we'll decide that later. So, goodness of fit. Here, the null hypothesis is that a given population is normal with mu equals 100 and sigma equals 15. So we're pre-specifying 3 things: the shape of the distribution and the value of both parameters. You may recognize this distribution as basically the way IQ scores are calibrated. I think the goal for IQ is to have be normally distributed. I think it's not surprising that intelligence in the human race is probably normally distributed. And then the test is calibrated, so the mean is 100 and standard deviation is 15. So maybe, you live in a community or work in a community, and your thoughts are that our community is not like the normal population, small n on that normal. That is, maybe you think your community is smarter or not as smart, whatever it is. And so you want to test the hypothesis. Does the standard way we think about IQ scores, does it describe my community or does it not? And so we set it up. If I have enough data for a normal distribution, I might use standard deviations above and below the mean to determine my segments. I didn't quite have enough data on this example. So notice our standard deviation is 15, but just so I get these tail probabilities fairly large, I made my segment sizes a little bit smaller than 1 standard deviation. And like I said, I think I said before, they don't have to be the same widths, because theta, the probability, will adjust with whatever the width is. But I kind of like to do it the same width, unless there's some really good reason not to do it. And so I've created 6 categories, 6 segments. I called them before. Less than 80, bigger than 120. Those kind of catch the tails. And then we have a separation of 10 values. And then I converted the z-scores. I didn't put the details here because we know how to do it. It's no mystery. The z-scores correspondingly are, you can see. And then from a normal table, I actually used Google Sheets. Whichever way you like to do it, I can find the associated probabilities. So for these z-scores, 4/3, 2/3, there's a 9% chance that a value was bigger than 120 given the null hypothesis, and so on down, 16, 25, and on down. And the nice thing about having normal here is that, once we set up our segments, as long as we pick the hypothesized mean, or X bar if the mean is not specified, then, and we keep the same segment size, then once we calculate the probabilities over here, we know them over there because we have symmetry working. If the hypothesis was that the population was, say, exponential, then, you know, we'd have to calculate the probability for each of our segments. Not that we couldn't do that, but we'll take advantage of symmetry when we can. All right, so I think the next thing, what did I write at the bottom? Oh, forget that. In fact, let me help you forget it. I decided at this point to just go to Excel. So let me share with you my Excel desktop, or Google Sheets, actually. So here it is. Column, I've done a random sample by using capabilities of Excel, Google Sheets. I've generated a random sample of 60 values, which we will take as our sample size. You can see starting with 107.122 all the way down to the very last one, 100.960. And just glancing, you know, it seems like there's some values bigger than 100 and less than 100. They vary quite a bit. So, you know, maybe the null hypothesis is true. The very first thing to do on Google Sheets, we get our data in there, is to sort it so we can calculate our frequencies easily. So I just take my 60 values. I could have sorted them right over here, but I wanted you to see the raw data. And so here is the sorted data. And then I just count how many land in my 3 categories. So you can see over here, I have an F column for frequencies. And once they're sorted, it's super easy to do. The bottom category goes up to 80. So you can see there are 7 values. And then the next category goes from, if I click on, notice that's row 9. And the last row, this category goes up to 90. The last row is there. So if I take row 25 and I subtract, did I say row 9? Yes. We get 16 in the second segment, and so on down. I just count them up, nice and easy to do once we get them sorted. And so now we can see that there's a little bit of an issue with our data, maybe. That is, in order, there are 7 values. The F's, F1 is 7, F2 is 16, F3 is 16, F4 is 15, and then they start to dwindle away. F5 is 6, and there are actually no values in the 6th, which is above 120. Yeah, so we go down here and, you know, the biggest value, oh man, 119.5. Now remember, when we derived our chi-square statistic, we made, you know, a statement like for large N or something like that. And the way we measure that, I think I mentioned in an earlier video, is we want our expected values to all be at least 5. And if they are, then we feel good about things. And so, you know, maybe whoever made this problem up engineered it just so that all of the values were bigger than 5. If that were not true, then we would combine adjacent categories, segments I call them, and adjust theta accordingly. Now theta would be the probability in being in either one of those segments. And so we make the adjustment, and then we can proceed as above, no problem. In the process, if I reduce segments, I've reduced my degrees of freedom, right? So it'll impact the result at the end of this. All right, and then we just get our expected value, which is theta, which I showed you earlier from the Z, the normal table, or I actually used Google Sheets here, norms inv, N-O-R-M-S-I-N-V. Yeah. The formula is not embedded here. So, and then we multiply theta times N is 60, remember? Theta times 60, and I get these expected values. And of course, they're symmetric because the null hypothesis says it's a normal distribution. Those are the expected values. And then we calculate our chi-square contribution. And this formula is inside here. We take F minus E. Oh, look at that. Well, the F's are in column E, not column F. Anyway, F. That formula looks wrong to me. Let me make an adjustment here. My frequencies are in column E. So if we want to subtract F minus E, you can see they're highlighted. Perfect. So that'll make a little bit of a difference. And copy down. Yeah. So the categories, you know, in the first segment, we're expecting 5.4, we got 7. Now we missed by a little bit, but not so bad. And the chi-squared contribution is small. The last category you can see is horrible. We got none in there. And we were expecting 5.5. And so we get a big contribution to the chi-square distribution. Now we add all these guys up. Man, look at that. Segment 4, we nailed it. We expected 15 and we got 15. So now we sum up our chi-squares and we get 11.56. What does that mean? We can't tell. A raw chi-squared value doesn't mean much to us. And so I calculated p-value. And we see the p-value is 0.07. So not less than 5%. So we're going to reserve judgment. Okay. There is some evidence here that the null hypothesis is wrong, but not enough evidence that we would just flat out reject it. And now let me tell you, I believe, if I remember right, I didn't write it down anywhere, to generate these numbers over here in column A, I used a mean of 98 and a standard deviation of 13. So I undershot it, and you can see we get kind of a bottom heavy distribution here, but it's not enough that, you know, we can't just rule out the differences by noise in our data. I mean, 0.07, yeah, maybe, but it's not like real convincing. And so we conclude our test. And let me go back to stop sharing. And let me pause this. And I may have one more example. I'm thinking that would be instructive to run this test, only test that the distribution is normal and not pre-specify mu and sigma. Okay, I don't think I'm going to do it. I want to run a non-symmetrical test as my second example, but let me say what you would do. From the data in the spreadsheet, you would calculate S bar and you would calculate S. And then you could use the same categories or you could compute new ones. If you use the same ones, then it will take you just a little bit. It's trivial, but you would need to adjust our thetas. I mean, the nice thing about using these segment divisions is that we can get the z-score just boom, that fast, and then we can get the probabilities. And when we use data, X bar and S, the values aren't quite so nice. They're not integers, but still we can convert to a z-score. You know, an easy way to do it maybe would be to only use 4 segments and have your 4 segments be below 1 standard deviation below the mean, between 1 and 0 standard deviations below the mean, between 0 and 1 standard deviation above the mean, and then more than 1. That would be 4 categories. The expected values would be all bigger than 5. It's the reason I cut it down to 4, and then you could just count the values and run the test. We have fewer degrees of freedom if we only have 4 segments, but I think it's a good way to do it, and you should get a huge p-value. Maybe I'll do it and just show you the result and not record all the details, because that would be using, you know, the way I generated the data to begin with. All right, so maybe I'll be back shortly with a non-symmetric example. All right, so here is the example I want to talk about. It'll illustrate a few differences from the first one. The null hypothesis is that some population is exponential. Lambda not specified, just is it exponential versus H1, it isn't. Okay, so let's just go to Google Sheets. See what we can figure out here. All right, so as before, column A is the raw data. And there you can see the formula I used to generate it. Doesn't really matter. That's not what we're talking about here. And so in column C, I just took the raw data and I sorted it so that we can do a quick and dirty count. Those values didn't change. Yeah. So looking at the data, I can scroll down and show you, you can see a lot of values below 1, a lot of values between 1 and 2, and a lot of values. But maybe what you'll notice is that as we move down, they get a little sparser. Like only 1, 2, 3, 4 values between 6 and 7, and so on. And then we got this weird sort of outlier here, 16. So looking at that data, I'm going to make my segments just a little bit different. You'll see I'm going to count, there are a lot of values between 0 and 1. What I want is the expected value to always be bigger than 5. Now, to know that exactly, we have to do a calculation, but just kind of eyeballing the data. We're going to make this decision. My first segment is all the values that are between 0 and 1. And I actually counted them up over here. I found 27 of them. I didn't actually check my work. If we sum these guys, we should get 100 if I found all of them, if I counted them correctly. Well, and if I know how to do the formula. So sum these guys up. 100, perfect. Kind of bugs me. I'm not really OCD, but it kind of bugs me to not have these guys all lined up carefully. All right, and then again, just counting the numbers between 1 and 2, 2 and 3, so far so good. But because they got sparser, I decided to make my fourth segment go from 3 to 5. And you can see in terms of the frequency is a good decision. We got 15, the same number as that one, reasonably comparable to those. And then my last category is just everything bigger than 5. You saw the way the numbers trickled out. That was like a good one. And again, we have a super great number, 18. So all the expected frequencies, look like I've made good choices. And the next thing is to calculate theta, the probability of landing in these. Now, notice, remember the hypothesis did not specify lambda. And also remember that lambda is the mean of an exponential population. And so because it's not specified, we're going to use our very best estimator for it. And that's going to cause us at the end to lose a degree of freedom. So of course, because lambda is the mean, our very best estimator of it is x bar. And if you calculate x bar here, I feel like I did, but then I think I thought it was extraneous and I erased it. Average, let's go C1 all the way down to C100. I don't think I mentioned there are 100 sample values. So X bar is 2.916. I think I used 2.92. Given that value, then I can calculate just with the quick integral. I used my TI-89 to do it. Once you set the function in, all you have to do is change the limits, 0 to 1, and then 1 to 2, and so on. And these are the theta values that I got. Per segment, 29.205, 0.146, 0.177, and finally 0.18, all super good values. I feel like my segment values. And again, let me sum those. It may not be exactly 1 due to rounding, but it ought to be close. Yeah, pretty close. We'll feel good about things, except these guys are so rebellious. Actually, let's like do this just in case. Sorry for being so silly. All right, and then we calculate our expected values, which is just going to be n 100 times theta. Boom. Because 100, we can do these in our head, but then they wouldn't be in the spreadsheet. And finally, we get our chi-square. Lost my C. So we're going to take expected minus frequency. We're going to square that, and then we're going to divide by expected. I should have observed that all of our expected values are safely bigger than 5, so no collapsing of segments. And now we'll just copy down. 0. Oh, because it was perfect. 18 and 18. Now let's copy this summation formula over. And there's our test statistic. That is teeny tiny. So let's do a p-value, although it's sort of chi dist this test value with how many degrees of freedom? Well, we have 5 categories, but we replaced mu with an estimate, so 4 degrees of freedom. Look at that, 82%. I think we're in love with the null hypothesis here. So we can fail to reject with emphasis. So with emphasis, 3 exclamation points, bold, and italics. That's what you do when the p-value is over 80%, maybe. All right, that's it. This is Thursday morning. By Friday, hopefully, not too late in the day, I'll have some homework posted for you. All right, have a wonderful weekend. We'll talk to you next week.